the skew between the two is within bounds. So the delay for S0 to Si minus the delay from S0 to Sj is within bound or should be 0. Okay. So now as I am saying that there are two parts. First is that total skew, as I know, because there is a device mismatch, I am going to insert the buffers. So there would be device mismatch, I will have a skew because of device mismatch, and there can also be a skew because of the wire mismatch or the segment length or width mismatches because of process variations. So there are two parts, and let me say I try to budget my total skew initially. So I can say the total skew TS will be nothing but a part of with buffer mismatches and other part with the wire mismatches. So TS B plus TS W, how much proportion you give to each depends on you. Here I would be assuming nearly 50% for each. Okay. So if it is now, I need to keep my, because it's segment, first of all I need to take decisions on my segment design. Segment means the wire design, because every segment then a buffer and a segment and a buffer. So first of all I am looking at my segment. I am trying to take some decisions, some informed decisions based on my segment dimensions. Okay. So now as I said, I am considering a kind of a path where you have a structure like we have a source and we have two destinations. Okay, and the wire is such that there is a split. The kind of modeling I will do for delay modeling is like an RC delay for this, an RC modeling for this, and an RC modeling for this. So kind of a structure in this fashion. So this is the delay modeling of this interconnection. Okay, and I have a source S0 and two destinations S1 and S2. Every segment length you can model like a pi circuitry or you can model like a T circuit. Okay. So every model, and then this would be driving, this whole thing will be the C load for the segment length S0. So that is the load coming at this point will be the loading for this segment. Similarly, there would be loading here and there would be an external loading over here, which are shown as CL1 and CL2. So this is how you will have a delay modeling of your segment or this wire. Now remember, I am going to now distribute my clock signal. I have to now design this circuitry because signal is going to pass through that. Clock signal is going to pass from S0 to S1 and S0 to S2, and we want to ensure that the skew between these two is either 0 or within the bound value. Okay. So now I need to know, there are two things. First of all, I need to determine the locations at which I should be inserting the buffers. So I will be determining the buffer insertion points or BIPs. It's very simple. Normally we go by equal path length approach. Okay, and then we go on increasing the number of buffer insertion points. So when I insert my first buffer insertion point, it would be nearly half. So total path length from here to here, you make it a half, so it comes somewhere here. So similarly from here to here, so this would be my first iso radius. So I would be inserting a buffer here and I'm inserting a buffer here. This is known as equal path length approach. So I call this as an equal path length approach for inserting the buffers. So like here, equal path length approach. Okay. Another is that we are not going for the iso radius. We are not going for equal path length approach. We are going by level. So if my circuit is having a split here, it is getting splitted up over here, so I will put a buffer here. It is further getting splitted up here, I put a buffer here. It is getting a further splitted up here, I put a buffer here. This is getting a split only at this point, so only one buffer. Can you see this path from here to this destination has only one buffer, whereas this path from here to this destination has 4 buffers. So we are not here, we are not going by the equal path length approach, rather it is a level by level buffer insertion points. Normally what we follow is equal path length points because it leads to a minimum skew. We get through this. So buffer insertion point is very simple, that you find out the first, normally you take the half point, that is your first cut line, and then we put a buffer over there. So wherever it is coming, I put my first iso radius is here, so I put a buffer here, I put a buffer here, I put a buffer here. I compute the skew. If the skew between two points is not within bound, I increase the cut lines. I increase the number of cut lines from this to, so now earlier there was only one cut line, now I have 2 cut lines. Equal path lengths are taken every time, and then you will be placing buffers at the cut points. Here, here, here. Still again compute the skew and still not coming within bound, increase the cut lines. So normal approach is this, by where we follow the equal path length approach. This is how we determine, very simple way of determining the buffer insertion points. Now whenever you put a buffer here, that means I need to design this segment and I need to design the buffer, and I need to design the buffer here, and I need to design the buffer also here. So we need to see the designing of a buffer and designing of the segment length, so that skews between any two destination, from here to here, here to here, between these two, they should be within the maximum value permissible. Within the maximum value permissible. So whenever we design a wire segment, so buffer design we will come a little later, everything is guided by the skew limit. What's the maximum permissible skew permitted? So now when you are designing a wire or a segment, it's a wire. It's a wire. It has a length, width and thickness. So normally thickness we do not touch because it is decided by the technology. So what are the design variables? They are length and width. Okay, length is mostly decided by the buffer insertion points, because we are going for the equal path length approach, so it is decided by the buffer insertion point. So what is remaining is the width. So now I need to take a decision on the width. Should I go for minimum width? Should I go for twice the width? Should I go for maximum width? What should I do? Okay, because when the width changes, suppose the width increases, then the resistance decreases but capacitance increases. So now I need to take an informed decision. I cannot just say, okay, let me take a minimum value, let me take a max. There should be some justification for that. Why am I going for that decision? So we now take, here we will be taking the process variations into account. So we will try to see the delta TS, because of the wire, it should not be a very large value. And it should happen because delta W would be changing as part of process variations coming in during fabrication process. So what we say is that, I say, okay, there are two destinations, S1 and S2, and there's a common source. Okay, and now I say that between clock signal is routed to S1, it is also routed to S2, and there is an equal path length. Okay, but I want these 2 points to have minimum skew or within skew limits. Okay, so I try to, what's the skew? Skew is the difference in the arrival of the signal waveform, clock waveform. So I try to find the delay for this path and delay for this path. If I go by Elmos delay formula, it is simple, R and C. So I have the S1, so R1 into CL1, because this segment will be driving a certain load and this segment will also be driving a certain load. So let that resistance of that segment is R1, driving a load CL1. You may put 0.7, you may not put 0.7, it hardly matters. It will be a constant. Okay, so R1 into CL1 with the first destination point, delay of the first destination point, and delay of the second destination point is minus R2 into CL2. 0.7 you can multiply, it hardly affects your decision. Now I represent this R in terms of rho L by A, or sheet resistance into L by W. So if I say sheet resistance is R, or you can say R sheet, this a small r here is not resistance per unit, it is a sheet resistance. So sheet resistance into L1 by W1. Okay, and here the sheet resistance again for R2 is written as sheet resistance, which is common. Sheet resistance is nothing but resistivity rho divided by the thickness, which is same for both the wires. So rho by thickness is the same for both the wires. So that is denoted by the same parameter. You may write it as R sheet, or here it is written as R, small r. So it is R L1 by W1 and this is R L2 by W2. Both are driving CL1 and CL2. CL1, CL2 may be same, they may be different. They may be different. Now this is the total skew which is arriving because of the wire part, not because of the buffer mismatches. It is because of the wire mismatches. And now I say that this TS will change. Now it's this, because it is a nominal value that I am writing, but because the dimensions may change in process variations, so my TS will have a variation. And I want this variation to be minimum possible. Okay, because I want it to be closer to the value that I have budgeted. So I am saying let that variation is, the skew variation is delta TS for the wire part. Okay, delta TS, and I want to find its variation with respect to, because I say CL I cannot change much and length I I have nothing to do here. All I can is I have to take a decision about the width. What should be my width? So I am now differentiating it with respect to the width. In terms of how does this delta ds, so we have to write it in terms of a Taylor series expression. Sensitivity to width, change in the width. I hope you all understand. Okay, so we are finding out the sensitivity of Ts to the change in width. So it is represented by a Taylor series expression. So it comes as in terms of change in Ts with respect to change in W1 into change, delta change in W1. So differential into delta change and differential of Ts with respect to W2, because W1 change and W2, they are independent. They are not correlated to each other. That is delta W2. It is a sensitivity I am computing of Ts with respect to the wire width changes coming due to process variations. Now this delta W, I know process technology can give me the highest limit 10%, plus minus 10%, or plus minus 15%. That is normally things are known to me. Okay, so this delta W can be, I know it can be plus 10% or plus minus 15%. Okay, plus minus hardly matters to me, because what I do is to get the worst case value, I always add up. Plus minus hardly matters to you, because we always get the worst case value. So we always add up things. Okay, so now I say this Ts by Tw1, I have the expression for this with me, which I find it out from here. So differentiate this expression with respect to W1 and differentiate this expression with respect to W2, keeping other things constant. Okay, and then substitute, and then substitute. So when you substitute, this delta Ts now becomes this expression in terms of CL1, L1 and W1, because you are differentiating with respect to W1. So it is W1 square and delta W1. Okay, so this is the variation in Ts. Delta Ts you are getting as a result of wire width changes happening because of process variations. So wire width changes may be happening because of delta W1. It can also be happening because of delta W2, both independently. So total things are adding up. Total things are adding up. Okay. So once we know that now, if I say that this is plus minus 15%. Okay, so this would be 15% of your nominal value. Whatever nominal value you have, changes can be plus minus 15% about that. So it comes out to be 0.15 into W. And W, and this is W1 square, it cancels out, it is only W1 coming in the denominator. Okay, because you would have a W1 here and W1 square here, that gets cancelled out. And now I can see that delta Ts is now proportional to this expression, where this is a number which is coming from the technology part. Okay, L1 is your length of the segment, CL1 is a load driven by the segment, and W1 is the width of the segment. Which segment? The segment between S0 source to S1, and this is a segment between S0 to S2. Okay, now you need to decide what W1 you want. So now it helps you in making decision. Variation in skew, wire skew, it is inversely proportional to W1. So I immediately try to feel, okay, let me have increase the W1. Let me increase the W1. Okay. If you increase, and also it is directly proportional to L1 and CL1. So reducing the path length and reducing the load and increasing the width helps you in getting a reduced delta Ts. But remember, here in CL1, this is true only if we are taking it as an external load. If we are taking it only as an external load. Okay. Now remember, I am making a decision here for the entire tree that I am going to design, clock tree that I am going to design. I am going to have a common strategy on wire width throughout the tree. Should it be minimum? Should it be twice the minimum? Should it be thrice the minimum? So that I would be fixing once I make this decision. So naturally, this segment is driving a further segment on that. If I am increasing the W here, the W at further points will also be increased. That means the CL which is coming off these followed up sections, they will also be increasing. So CL1 is actually having an impact of increased W. So naturally, if I say the parallel plate capacitor epsilon A by D, the D is a thickness, epsilon is a permittivity, A is simply L into W. So for this segment driving next section also has a twice the W. So CL1 will also get doubled because of W becoming twice. Okay, so that two factor, and here my segment length is also becoming twice. So increasing W actually does not give you any benefit. Increasing W actually does not give you any benefit. So that means increasing W actually has no benefit to you. Why should I increase my area? It is actually not reducing my delta TS. It is not helping me in reducing my delta TS because that is getting impacted in terms of, it is coming back to me in terms of CL1 or CL2. Because my tree is not stopping here. Tree is spanning in a forward direction. So I have to take the total scenario into my account. So I am saying, okay, increasing W does not help me. So why should I increase the area unnecessarily? So let me have a minimum W. So here I have taken the first decision that throughout the tree design, I would be keeping the segment width minimum value. I would be keeping the segment width as the minimum value.
If there is, let's say, crosstalk between wire 1 and wire 2, will that affect
crosstalk? I am not considering right now. Crosstalk comes in terms of noise. Noise. Crosstalk is a form of noise. Okay. So here I am saying only, yes, it is a, you can say, one of the issue. So normally crosstalk is resolved by separating the wires. Because the moment wires are separated enough, the crosstalk reduces drastically. Or between two wires, we place a ground rail. So that mutual coupling gets reduced. It gets eliminated. So there are techniques for reducing the crosstalks. But then certainly, even by when you are inserting a ground rail, okay, still the wires are becoming apart. You are increasing the distance between the wires. The only strategy which is very good enough is split the wires apart to reduce the crosstalk. Okay, but then sometimes it is not possible to have them too much far apart. Okay, then if making them far apart is not possible, bring them together and place in between a ground rail so that you can reduce the mutual coupling. Because crosstalk is because of mutual coupling between the two conductors. Inductive and capacitive effects comes into picture. Okay. So here, as I'm saying that I'm not looking at those noise issues currently. I'm looking only at transmitting my clock signal through a tree, and design of a tree, that's what I am looking at. How to design the tree, and my guiding parameter is the minimization of the skew between any two destinations. Okay, when I say minimize means I know what is a permissible value. I have to bring it less than that. It should be less than that. Ideally, value is 0. Ideal. So here I have taken the first decision that I would be keeping throughout the tree my wire segment width as a minimum value. Okay. So now first decision I have made. Now next is we come to the segment length. Segment length, as I said, is determined by buffer insertion points. And if you are following the equal path length approach, the L gets automatically set following that algorithm. Okay. So whenever now, how many buffer insertion points I need? Where to stop? So that means I have to, that is, as I said, it is guiding parameter is a skew. So every time I have to go on computing the skew. So once you have the first isoradius, compute the skew. You are not satisfied, increase the isoradius level by 1 and then again compute the skew. You can do it by using a computer software. You can write an algorithm. So that is why all clock routing algorithms, they are normally done by the software. It is not done manually. Because here I can do for 2 points manually, but think of millions of points, it's very difficult to route a clock tree. So normally everything is written in the form of a software, and then it is a software which takes care of deciding a clock tree. Every time it computes the skew, and if it is not permissible limit, it increases the isoradius level by 1. Okay, so now we will understand this algorithm by looking at a very small section of my wire clock tree part. So okay, so what we say is that I have a path. Okay, what is this? Yes, S02. Now this is suppose I am taking a sample of my clock tree from source, and there are 4 destinations. Okay, so signal is moving from here to here. Clock signal is also moving from here to here. Clock signal is moving from here to here. So there are 4 destinations. Now if I am computing the delay from S0 to S1, and I am also computing the delay from S0 to S2, so my skew difference is the delay arrival, the clock arrival between these 2 points. I will do this, repeat this for S1, S2 pair, for S1, S3 pair, and for S1, S4 pair, then for S2, S3 pair, S2, S4 pair. I will keep on doing, because every point should have the skew within bound. Every pair should have the skew. I am not talking of a buffers here. It is simply the wires I am looking for. Still it is a TSW I am looking for. Okay. So here is how to compute the skew now. Now aim is to define a strategy for computing skew. In what way you will compute the skew? So skew is the difference between the, as I said, the clock signal arrival here and here. So what's the worst case skew possible? That is, it takes minimum time for signal to reach here and maximum time for signal to reach here. That will be the worst case skew. Okay, so now I have to find out the values or the setup which I should use for computing the best skew and the worst skew through a path. I have to find out a setup for myself. In what way I should compute the delay? That will be the maximum delay and the minimum delay. So as I know, delay is simply RC product. So worst case delay is R maximum, C maximum, and the best delay is R minimum and C minimum. Okay, now here is that I have taken one decision that width will always be minimum possible. Okay, so width is fixed. Okay, so width, suppose I am computing from S0 to S1. So that means my on path is from S0 to S1. And all other paths are off paths, offline paths. They are connected at this node, but I am not concerned about the travel of clock signal through this. So this becomes my off path and this becomes my on path, because I am computing the delay from S0 to S1. So this is my on path. Now the best delay means resistance through this is minimum, resistance through this is minimum, and capacitance at these nodes, because this segment will be driving, I would be maybe putting a, so this is one segment, I may be putting a buffer here, this is iso radius, and then the next segment. Okay, so here the load for this is acting as the capacitance for this is nothing but it is a load for the first segment. And also there is a split point. There is a split point. So what I want to have for the best delay, all loading attached to my path from S0 to S1 should have minimum C. It should have minimum C, which is coming from off the path. It has its own loading plus the loading coming from the split points. Plus and it is the best delay I am looking for. So resistance is more or less fixed for me because I have fixed my W, but then off the path I should have, I am able to change my W. The best situation, because what will happen is that W will change, plus minus delta W will happen. Okay, plus minus delta W. So that will cause, if I say plus minus delta W, so what strategy I should have for the best delay? That means the resistance should be minimum and the capacitance coming from off the path should also be minimum. Okay, so that means resistance should be minimum. That means resistance will be W plus delta W. Process variation is happening. W plus delta W, and this capacitance should be minimum. So it must be W minus delta W. That means this length, this wire should have a wire width W minus delta W, and this segment should have a wire width W plus delta W. This is for best. For worst case, it is a reverse. This resistance must be minimum and capacitance coming from here, this resistance must be maximum. Worst case situation, and the capacitance coming from off the path is also maximum. So I am increasing the width here. I will increase the width here and I will decrease the width on the line. I will increase the width of the line. Okay, so worst case, as it is written worst case, so can you see that worst case path, this is my on path, so it has a minimum W, but all the off paths, they have larger Ws. So I'm maximizing the delay. I'm going for a situation to maximize the delay. And then I compute. I can compute by using simple Elmos delay model for manual calculations. If it is too sophisticated, you can write a computer software. You can use a more advanced delay modeling to compute more precise value through the wire. Okay, so once we have that strategy in our mind, now I can compute. Okay, so what all I should do is that, so first is for worst case arrival, that is a worst case delay from S0 to S1. It is simply R along this path into C at, total C you can compute now. So C attached here and a C attached here. So C along these paths. So we can find out the total D as simply, now remember, the D is, the wire is driving itself plus wire is also driving the external load. Wire is also driving the external load. So for any segment, the total delay given by Elmos delay formula is simply the R of the segment, the C of the segment. We know ladder network formula. So RC by 2. RC by 2 plus it is also driving a external load. So it is R into C external. Got it? So I will have, now you can model it. Remember, you can model it like this. I think I have shown you the solution, the expression over here. Yes. It is like the segment R driving the capacitance C1, it is also driving the capacitance C load. So the delay through this wire, which is simply R1 C1 by 2, and then the delay coming because of driving this C load 1. So it would be R1 into CL1 added to it. Clear? So I can do this for finding out the delay for if you are putting a buffer here, the buffer will give you a capacitive load. So it would be one segment driving a capacitive load, another segment driving a loading over here. So total delay will be addition of the two delays. Okay? Clear? So this I will find out my worst case delay. For best case, I will do the reverse. I will make this wire thick over here and all other wires thin over here. Repeat the same process and find out your best delay arriving at S1. Now do this for S2. Do this for S3. Do this for S4. Now to find the worst case skew between the two destinations, so I have to choose the best here and the worst here and subtract the two. Do this for every pair of destination. You will have a database ready with you. You will have a database ready with you which you can analyze that wherever the value is exceeding, is there any pair for which the skew is exceeding the permissible limit? If it is exceeding, that means increase one isoradius level. That means it is not satisfied. Increase one isoradius level. And then again repeat the same process. So this is where I am designing my wire segments. So what I have done is that I am determining the length of the segment by determining the number of isoradius levels, and also by looking at the process variation sensitivity to my skew, I am deciding for my wire width. So I have decided for every segment the length and width. T we do not change. T is usually set by the technology chosen. Okay, so TSW I have taken care of. TSW. Now there is another component called TSB. B comes from buffer. Because I would be inserting a buffer over here. So my total delay is not only because of segment, it is also because of addition of T buffer. T buffer. Now if T buffer is mismatched, I will get a skew. So this T buffer skew should also be within bound. So I am attacking every point separately. I am attacking TSW separately and I am addressing TSB separately by doing proper skew budgeting initially. And then I will combine the total effect and will get my total skew TS less than the permissible value. So now if there is a TSB, I have to look at. So if it is a TSB, I have to look at. So I now look at only buffers. I will not be looking at the wire segments now. I will be looking at the buffer design. Okay. So first of all, now buffer can be even numbers, buffer can be odd numbers. You can have even number of buffers, you can have odd number of buffers. That is not my concern. I'm actually looking at a strategy. You can adapt the process to even number or odd number of buffers. Okay. Now I say that what can happen in device. Why device mismatch? What happens when device mismatch happens? Device becomes either slow or device becomes fast. So either it becomes slow or it becomes fast. Because of that, because different inverters, some NMOSes can become slow, another NMOS can become fast. So even if I am designing them equally, I may have a pull down delay mismatch, I may get a pull up delay mismatch. I may get. So let me characterize that nominal rise time and fall time, nominal high to low delay and low to high delay, rise or fall delay. So TR is my nominal, and TF is my nominal. Then I say, okay, what happens if it becomes fast? Then TR for fast device becomes TR by a parameter which I am calling as FP, a parameter. For PMOS it is FP, for NMOS it would be FN. So that FN and FP may be different for each device. So I say if the device is becoming slow, my NMOS is becoming fast or PMOS is becoming fast, that means nominal value will be less than, the delay will be less than the nominal value. So my delay for a fast device will be TR, F for fast is TR by FP. And if it is a slow device, it will be TR, slow will be TR times FP. Now you may argue, madam, FP may be different for both the cases, okay. But here I cannot tackle everything at the same time, I am taking one by one. So here I am assuming the parameter is same, by which the device is becoming slow or the device is becoming fast. Okay, so now I say because of process variations, the device is either becoming slow and fast. So change in rise and fall delay, TPHL and TPLH will be defined by these relations. Same relations I can define for my NMOSes, where FP will be replaced by FN. FP will be replaced by FN. Now you can take any example. Suppose there are two paths from source to destination. Purposely I am taking two equal paths so that wire segment delays are not affecting. Okay, what is coming in the skew variation is because of the buffer or device mismatch. Purposely we are taking equal paths, equal. So three buffers in the path and here also three buffers in the path. Okay, so source to destination S0 to X1 or S0 to X2, this also has three buffers and this also has. Now it can have two buffers also, four buffers also. It is immaterial. We have to look at the strategy. Okay, so you can have two buffers also, as I said. Okay, now here is, if it is a two buffer, it would be one pull down and one pull up delay. If it is a three buffers, it would be say two pull up and one pull down, or two pull down and one pull up delay. So you will be writing the delay expressions accordingly. Okay, so now if I have the two paths, so D1 path, so where you have three buffers, I will be writing the expression as D11, D12 and D13. For the second path, it would be D21, second path first inverter, second path second inverter, and second part third inverter. So total delay D1 and D2 will be given by these three expressions, where D11 correspond to first inverter, D12 correspond to second inverter. Now it depends, D11 and D13 may be pull up and D12 may be pull down, or the reverse. D11 and D13 can be pull down, depends on the clock signal waveform, and D12 can be pull up. In any situation, nominally I want D1 minus D2 to be 0. The skew to be 0. I want D1 minus D2 to be 0. Okay, but it may not happen because of the slow and fast devices that we are getting due to process variations. But my requirement is that even if there is a process variation, what should I do to have D1 equal to D2 or D2 to be within a normal TSB, within a permissible T skew buffer? Okay. So if I say if there is a slow and fast devices coming up, how I rewrite my expressions? So my rewriting expression D1 prime, it is a modified delay for the first part. So D1 prime will be, now it will be first becoming fast. So when I say all slow PMOS and fast NMOS, suppose this is what I am taking. How to write? Suppose my PMOSs are becoming slow and NMOSs are becoming fast. In that situation, how to rewrite the expression? D1 will be, so it's a pull up. So this is slow PMOS, pull up, 2 pull up and 1 pull down. In that situation, FP times D11, FP times D13 and pull down will be D12 by Fn. You can take any combination and write the expression. When 2 pull down, 1 pull up, you can write any expression. Okay, similarly D2 prime will also be written like that. Okay, this would be FP, D2. Now we are assuming that the paths, because they are closer. The paths are closer, that's what I say, local skew is between communicating blocks, so they will be closer. So when they are closer, that means their process variations will be more or less same for both. Process variations will be same for more or less both the devices because they are in close vicinity to each other. The way one is getting affected in the same way, second is also getting affected. Okay, so we are saying in the same way, so FP, D21, and this becomes D22 by Fn, and this becomes FP by D23. Now in this situation, if I want D1 prime minus D2 prime to be 0, it should be equal to D1 minus or, so D1, so now what I am saying that D1, that nominally your values will be equal. D1 equal to D2, but because of fast and slow, D1 prime is not same as D2 prime. So still I want the D1 prime minus D2 prime to be equal to D1 minus D2. Because D1 minus D2 may be some value. It may be some skew value. So I want, even if there is a process variation happening, the difference between the two delays should be the same as D1 minus D2. Even if there is a process variation happening. So if it is to be same, that means individual terms, they have to be the same. That means I should have the pull-up delay in my modified delay expression should be same as the pull-up delay in my nominal delay expression. And pull-down delay here is same as the pull-down delay in my nominal delay expression. So that means if this is pull-up, these two are pull-up. So, okay, these two are pull-up, or individually the terms, they must be same. Individually the terms must be same. So the 2 pull-up must be equal to 2 pull-up, and this pull-down must be equal to this pull-down. Or in the case of process variations, these two should be same as the nominal ones, and this must be same as the nominal pull-down. Then you can ensure that even under process variations, the skew will be met. The skew constraint will be met. I need not have equal values for individual inverters. That is not required. You should not have equal pull-down delay. That you cannot have because devices are becoming slow and fast. So you need to ensure that the summation is equal. Summation means here the subtraction is equal, or individual terms are matching. Individual terms are pull-up and pull-down delays are matching. So how to design in that situation? So designing this is one problem where we are expressing the general concept by using 3 inverters. But I will take first a very simple case where I have only 2 inverters, where I will have only 1 pull-up and 1 pull-down transistor. Sorry, 2 inverters, 1 pull-down delay and 1 pull-up delay. And we will try to get some design strategy which we can apply to this one. A more general case with some few more additional complications. But let me derive it for first very simple case where my source to destination path has only 2 inverters. Minimum possible inverters, that's what I am saying. Okay, so that I come across only one pull up and one pull down delay through the path. I'm doing it just for that case. So now you have two destinations and there is a common source. So destination is I and J and source is S0. So S0 to Si and S0 to Sj, and every path has two buffers. This two buffer and this two buffer. So this will also have one pull up, this will also have one pull up, this has one pull down delay, this also has one pull down delay. In any situation, the Di path is Di pull through PMOS and Di pull down through NMOS. And Dj will also be Dj pull up plus Dj pull down, and I want Di minus Dj to be always less than Ts, to be always less than TSB. So now I do a budgeting because there is a pull up separately, there is a pull down separately. I budget half of my TSB to pull up delays and half of my TSB to pull down delays. Can you see the reason why I am choosing only two inverters? Otherwise, I would have been making, suppose it is three inverters, pull down delay will be more and pull up delay may be less, or the reverse. Pull up delay will be more, so you have to budget accordingly. You have to make 3 points, then 2/3 should be given to pull up and 1/3 should be given to pull down. Here I would be giving 50-50% to pull up and pull down. That's the only change. That will be the only change. As I said, whatever you design here can be, with some modification, you can apply it to more number of inverters in the path. Okay, so now I say that okay, DPI and DPJ must be TSB by 2. 50-50% I am allocating, and DIN and DJN must again be less than half of TSB. Okay, and now I introduce the fast and slow devices concept. I write my DJ, so one path, worst case condition, one path becomes very slow and one path becomes very fast. All devices become slow in one path and all devices become fast in one path. Worst case condition. So suppose the DJ is becoming slow. The JH path is becoming slow. So it is FP, DJP plus FN, DJN. Both transistors are becoming slow here and both transistors are becoming fast in the ith path. Worst case skew conditions we are taking. So here both are becoming slow, delay is increasing, and both are becoming fast, the delay is decreasing, and I say that Di minus Dji compute. I write the expression for Di minus Dj, so this component minus this component. In terms of what is this? Pull up and this is pull down. And then you simplify. And then this value, the total Di minus Dj, each component is for less than TSB by 2. So now I separate the two terms and make a separate equation. One for pull up, other for pull down, and then I solve this equation. It gives me this relationship. Just take only one equation. Similar relationship you can get for second equals also. So when you look at this and try to solve it, it gives you this quadratic. It gives you this quadratic. So this must be either equal to 0, must be within less than, at the most equal to, it should be at the most equal to TSB by 2. Sorry, it must be TSB by 2. It must be a mistake. No, TSB by 2 has been taken care of. So it must be 0 only. I'm sorry, this I will remove. Because TSB by 2 has been taken care of. Okay? So it must be, equation must be on the right hand side, you must have a 0 only. And now we have this expression with me. So it is 0 here. So now you can decide, use this equation to arrive at what W you should have for each device, which minimizes your delay or the skew variation, or the delay, you can say, which keeps the delay within bound so that the skew remains within bound. What W you should have, so that ultimately the delays that you get because of that W keeps the skew within bound. Okay, so this is equal to 0, and now I say suppose my budgeted skew is 10 picoseconds. That is what I have. I know the value. If my budgeted skew is 10 picoseconds and my factor by which it is increasing or decreasing, slow and fastness is 2. Suppose it is 2. Okay, I substitute the expression over here. And then I try to find out a relationship. So for 0, is it a 0? Is it correct? For 0, I think you get this expression. From here you get this. That means DIP must be 4 times DJP, that is for pull-up. Pull-up means the PMOS, the inverter which is giving you a pull-up delay, and the inverter which is giving you a pull-up delay in jth path. That gives a relationship between those two inverters W's. Between the W's of those two inverters, that means DIP must be 4 times DJP. Now if my DIP is a propagation delay R into C, if both are giving you, so can I reduce this 2 in terms of W? If L is same for both, and assuming CL to be the same, then everything comes down to the W relationship. Which gives me that in the ith path and in the jth path, the 2 W's should be in this relationship. This will keep your skew within bound for pull-up component. Do the same thing for pull-down component. So I have now taken care of the buffer mismatch side. So now when you combine the two things together, you have to design buffers accordingly and you design segments accordingly and then run that complete simulation ultimately to get the total budget values, which should be within a very simple method, but just to give you an idea how a CDN is designed. Today's CDN are very, very complex, where very complex mathematical algorithms are used, like simplex method or Newton-Raphson method, they are used over there, where they try to do the designing, but everything ultimately to keep the skew within bound, but ultimately everything comes down to the designing of the transistors or the designing of the wires. But that comes with the guidance coming from the skew permissible limit. Okay, so here I have taken the worst case. Maybe you can do the same analysis for the other cases. Slow PMOS, slow NMOS in both the paths, or fast PMOS and fast NMOS in both the paths. You can do it. Now here is, I have not taken care of the power consumption. Because when you design here, my only guiding parameter is the skew. But skew is not the only thing. I have to also run my clock signal fast from source to destination, keeping power consumption minimum. So you can now make your problem even complex. That from S0 to Si and S0 to Sj, okay, the signal has to do 3 things. Design a CDN such that the signal takes minimum time to reach from source to destination, both the paths. And also, the skew between the 2 destination points is within permissible limits, and while maintaining these 2, the power consumption is minimum possible. So you can put more constraints. You can design it like a mathematical problem which has to be solved within constraints. Optimization problem. Anybody who has done optimization, he would be knowing. Make it a kind of a mathematical OR, operation research, or optimization. Anybody can define it like a optimization problem with constraints. Constraints, 3 constraints: minimum skew, minimum power consumption, minimum delay. And then solve it for W values which can lead to a minimum of all these 3. So it is basically a mathematical problem, optimization problem, optimizing between the 3. So various algorithms, as I said, various mathematical algorithms are used to define a clock tree or design a clock tree under a given set of constraints. Okay, So this is how we go about designing a clock distribution network. Now the next is how do we achieve minimum power. So okay, one way is that you design it like a optimization problem. There is something else I can do more than that to achieve a lesser power. So low power CDN, so how to design drivers or the buffers for low power, what should be done to achieve low power is something, because clock frequency you do not want to reduce. We do not want to reduce the clock frequency. Without reducing clock frequency, how to achieve lesser power consumption? Okay, so some techniques which have been published and which proved to be useful, we'll be discussing in our next class. I'll not be taking class on Saturday. Kindly inform your Goa campus students. I also put it up on Nalanda, but I think they cannot see Nalanda. So maybe I can